About page 343, we are talking about special right triangles and specifically, reminder, the 30, 60, 90 triangle theorem. If you don't have that note card made, make one. You can find it on page 343. We're going to kind of reveal the answer here as we go through this paper. The length of the hypotenuse in a 30, 60, 90 triangle is 2 times the length of the shorter leg, and the length of the longer leg is square root of 3 times the length of the shorter leg. There's a bunch of detailed information along the way. Let's actually figure out from our work on page 343, in order for us to figure out why those relationships happen. If you haven't done page 342 yet, please go back and watch that one. Please, make sure that you've processed the triangle on that paper, and we're also addressing a learning goal for this lesson on justifying some special right triangle theorems. Remember this lesson, it doesn't go away until you're done with pre-calc. Explain how you know that point C lies on the perpendicular bisector of AB. In order for us to study this, we need to go back and take a look at the picture of the triangle that's drawn when two circles overlap and they share a common side across the bottom. So this question from the other page says, how do you know point C is on the perpendicular bisector of AB? Well, it's because C is equidistant, which is why there's a spike and a spike. Okay, back on the original page, if C is equidistant to AB, C is equidistant vis-a-vis AC equals, or is congruent to BC, the B there. So that means that C is on the perpendicular bisector. Okay, the next question, what do you know about the lengths of DB and CB? So when we look at the picture that we have on page 342, what do we know about the length here across the bottom and this length over here on the side? Now remember, this is supposed to be an equilateral triangle where all of the sides are the same, and this line bisects or cuts AB in half. So whatever this length is, it's half as long as the full length, like a 2-to-1 relationship. If you're not convinced, you can measure it. So I'm going to use centimeters. I'm going to measure that I get 3 centimeters, 0.2. I get 3.2 centimeters across the bottom. It should also be 3.2 centimeters across the side, and it certainly is. But if I measure just AB, just from D to B, this statement right here, I get 1.6 centimeters. In other words, this line segment is half as big as this one. So when I go back to DBCB, I can say that BC is 3.2 centimeters. DB is 1.6 centimeters. This looks like a 2-to-1 ratio. In other words, DB is half of BC, or BC is twice as big as DB is. All of this is our relationship of the short to hypotenuse sides of a triangle. All right. So the next up, Next up is that we're going to take that relationship. We're going to revisit the triangle. Absolutely, we can measure, but we have some other resources that a right triangle can use. Like, for example, what you learned in 8th grade. The Pythagorean Theorem, or whenever you did, the Pythagorean Theorem allows us to find the third side of a triangle. So in this lesson, we already have information for BC and DB that they're 3.2 centimeters and 1.6 centimeters. So we can use the Pythagorean Theorem, and whatever result we get, we can also confirm that it's right because we can literally measure it. So here's what we're going to do. We're going to bring in the Pythagorean Theorem into this problem. Let's go. I'm going to redraw the triangle right here. It looks something like this. We're going to put some labels. We're going to put some measurements. And then, of course, it means centimeters, but I'm going to drop the centimeters for this problem. And now I'm going to write what the Pythagorean theorem says. It says a squared plus b squared equals c squared. Well, this is meant to be c squared. So I'm going to rewrite 3.2 where c is. This is using substitution. It's still squared. It still equals. I'm going to say short leg should be a. So small, medium, and long. The short leg should be a. So I'm going to put 1.6. And then I'm going to square it because we're substituting this 1.6 for a, just like we did 3.2, is c. See, I kind of want to make sure that I'm visible. Sorry. Okay. We don't know what b is. We can use a question mark. We can use a variable. We can use geometry. This third side right here is b. And this is made up of this line segment, CD. So I can put CD where the b letter is from the Pythagorean theorem. It has to be squared. There has to be a plus sign. And now the goal right now is to actually end up solving for CD. And we'll compare that answer to actually measuring it. You want to, and again, not measuring this, but measuring the one on the other page. Okay, I need some help. Let's see, I can go with my calculator. And my calculator would be Desmos. So let's bring in Desmos to do some calculation. Here we go. Kind of like size it in the window. Desmos.com/calculator, great resource. Keep that around. And all I really need to do is just type, well, I could type the entire thing as it is, 1.6 squared plus, and then I don't want to type CD because Desmos is going to get a little bit tripped out. So I'm going to use X. I'm going to say equals 3.2 squared. You can just straight up type the entire expression into Desmos. Like, you can do that and it'll be fine. When you look at the graph is going to tell you what the answers are. So over here we have a negative 2.7. Also on the graph, kind of sliding the window over, we have a positive 2.7. And so it's important for us to recognize 2.7, maybe 2.8 if you round, is the actual answer, the actual solution. I'll show you what we need to do, like for the geometry here in a minute. Like, for example, I know that I could subtract 1.6 squared from both sides. That would give me x squared equals 3.2 squared minus 1.6 squared. I still wind up with the same result over here because these are the same equations. But because it's x squared, we should really try to use square root. And so I'm going to use square root to make the square on x go away. But that means that the entire right side has to be square rooted. By the way, I'm doing SQRT to force a square root symbol in Desmos. Or you can use a little keyboard. Okay, I'm going to type all of this, 3.2 squared. And then I'm going to keep the 1.6 squared also under the square root. And by the way, here's our solution with way more decimals than what the graph provides. So I can go back to my notebook and I can write that CD is 2.77. One more chance, go back. 2.771. CD equals 2.771. And if I measure the actual square, or the actual side of this triangle, I should see about 2.7, 2.8. Check it out. There it is. From 0, 1, 2, not quite 3. Back it up 2 millimeters. It is, in fact, 2.8 on the line. What I'm really trying to show is that the Pythagorean theorem will work. But what this textbook is wanting you to understand is we have a specific triangle. It's of a certain size, and this will always work, right? It's measured to be 2.8 centimeters. And so these are essentially equal. But what if you don't have a ruler? What if you don't have, or I give you a question and I say, nah, don't trust what I drew, trust the numbers that I put in there. Like, I'm not actually gonna draw a right triangle where the hypotenuse is 5 miles. I'm going to let a map kind of like show you like some scaled down version of it. So here's a different way of thinking about it. I can say a squared plus b squared equals c squared, just like before, right? Just like here we have 1.6 squared plus cd equals 3.2 squared, etc. Just like all of this filled out. But instead of filling out 1.6 and 3.2, I'm going to let them just be space holders. Because up above BC, that's the hypotenuse, I can write that right here, BC squared. B, just like it was over here, B is CD, so I can put CD squared. But I'm going to put A in, as it is the bottom edge of the graph. I'm going to put A and call it half BC. That's the reason of the trick that I'm going to use. Instead of writing BC and then, well, okay, Toya, I'll show you. These are the letters from the triangle. Like, this is the green edge, BC is green, and DB is orange. And the goal is still to solve for CD, but watch this strange math magic that's going to happen. I'm first of all going to substitute that DB is 1/2 BC. So I'm going to rewrite that instead of writing DB. And it should go in parentheses because there's a square involved. So I'm going to put the square outside. And this is just straight up a substitution based upon what we did up here, right? All of this, I'm going to replace DB because DB is highlighted orange. And it's what is that connection between how this number is twice as big as this one, or this number is half as big as this one. Okay, plus CD squared equals BC squared. The goal is to get CD by itself. Okay, so continuing on, if I multiply by, or not multiply, if I square, everything in the parentheses gets squared. So I'm going to have 1/2 squared, which is 1/4. Then the BC is squared, so BC is squared, plus CD squared equals BC squared. When we have all of these letters here, I'm sorry the letters are there and they're convoluted, we're going to make sure we have all of the BCs on one side, that way, right? On one side of the equation, leave CD on its own side of the equation. So minus 1/4 BC squared from both sides. That's going to give us CD squared equals, now I got 4/4 right here, so 4/4. And then I'm taking away 1/4, so minus 1/4. But it's of these things, right? I'm combining the numbers in front of BC squared, but there's nothing I can really do with the BC squared. I just got to write it down. Now you got to remember your fraction math. What's 4/4 minus 1/4? 4 minus 1, 3. Keep the same denominator. This becomes 3/4 BC squared equals CD squared. Trust me, this is wrapping up. We're about like 2 steps away from being done. Okay? And this long video is about to its end, and we can move on to the next page. Square root. Okay. Squares and square roots cancel. That's why I'm using square root. So the square and square root are gone, leaving me with just CD. And then over here, the square root is applied to all of those 1, 2, 3 things separately, because that's a property of square roots when you're using multiplication and division. We can square root the 3, we can square root the 4, but the square root of 4 is 2, and then we can square root the thing BC that is squared. So this square is going to cancel out with the square root when it's matched with it. This root 3 over 2 That's a relationship that exists for forever. And if we use the fact that we know what BC is, we know from our measurement that BC is 3.2 centimeters. So I can go ahead and use this formula to come up with another way to actually calculate that doesn't use Pythagorean theorem like we did. I can just put root 3 over 2 times 3.2, and I can go calculate this in Desmos. Here goes. Okay, here's all the work from before, but now I have square root, again it's SQRT, 3. If I type a 2 right here, the square root's over everything, so I don't want to do that. I want to go 1, 2 buttons of the right button to move the cursor outside, and then go divide by 2. See how the 2 is not inside the square root, but it's on its own side of the fraction, and then I'm going to pull times 3.2. What? They totally perfectly match. We did it right. That's how I know my calculation right here is correct. 2.771. All right, finishing it out. There is a theorem that I want you to have a note card made for this one. On the back of it is our picture. We have this relationship. I see square root 3 because I saw square root 3. I saw a 2 because we saw a 2. And so that is our connection. Thank you for watching this video. See you on the next one.